לא יודע, קצרה.
Sagie did his master's at Oxford, where he worked on computational logic. Then he joined the deep learning lab at Tel Aviv University. He was very prolific during his studies, working on deep learning, all aspects of deep learning. He also did an internship at Google, working with Bill Freeman and Michal Irani. And he's now a postdoc at the Pioneer Center for Artificial Intelligence, working with Serge Belloni on 3D, something a little bit different than what he did in his PhD. And this is what he's going to talk about today. The 3D reconstruction, inference in 3D, and how to apply deep learning to 3D. Thank you.
Thanks, Leo. Thank you for the introduction. I'm very excited to be here and talk to you. And so today I'm going to talk about my recent works towards a controllable generation of the 3D world. And so my research is in the area of generative models. And so in a very high level, we're given a sort of a collection of images and inputs, such as those collection of faces. And then we want to train a generative model to generate novel images, given some random noise. So in the unconditional setting, we just have some random noise and we output, for example, these images of faces. And in the controllable setting, however, we want to be able to add some control to the generation. So one way of doing that is by conditioning the type of distribution that we want to generate. So for example, by conditioning on this class of yellow flower, you only want to generate those images of yellow flowers. Another way of controlling the generation is by restricting it only to perform manipulation of the input. So this could be, for example, by a text, but we only want to manipulate a certain region in the input image. And this could also be via another image. So for example, we might want to transfer the mustache of the image on the top to that of the image in the middle. And another type of constraint could be that of output constraints, where you don't constrain the generation, but you also the target distribution, but you constrain the type of output that you get. So for example, here, if we get an image and we constrain the outputs to be only style changes of the input image. And so during my PhD, I mainly concentrated on 2D generation, that is generation of images and videos. And I looked at a number of settings. So I looked at the generation from a few number of images and videos, where you have to design useful inductive biases that capture the internal structure of images and videos. I looked at the problem of finding analogies between domain, where you're given an image in an input UN and you want to generate an analogous image in a target domain. I also looked at the setting of visual manipulation, where you want to adapt an input video or image semantically. So for example, on the left, adaptively speeding up a video, manipulating objects in a video, changing the essence or style of images. And I also looked at how these generative models can be used for downstream applications, such as those of mitigating bias and detecting a distribution shift. And so more recently, we have witnessed a revolution in generative AI. For example, you may have all seen these generative models that take an input text and are able to generate images. And this has really created a revolution.
Perhaps you can shrink the
zoom window.
The underscore. Just press the
It
doesn't show on my screen.
Okay, sorry.
Okay, so recently we've witnessed a revolution in generation, particularly for 2D, where we're given an input text as input and we are generating images, and this has really revolutionized the way we create art or perform design and so on. But we have yet to see this revolution in 3D. Okay, and so what do I mean by generation in 3D? In 3D, we are interested in generating, for example, different shapes. So for example, this shape of a chair. We might be interested in generating multiple views of a scene. So if I give them one view, I want to generate another view of that scene. I want to also be able to generate a deformable object. So, for example, this object of the dog, I want to be able to describe how the shapes changes along time. And I want to be able to also have a control of the textures of objects, the materials of objects, as well as the physics, how they interact and move around the world. And so doing so can really have, I believe, transformative applications for almost every industry in our life. So just to give a few examples here, if we look at that of design, we could intuitively design our home by generating and manipulating objects in our living room. We could look at that field service where we might want to manipulate certain objects and see the effects they have when we are fixing certain objects. In healthcare, the ability to visualize the brain while performing an operation. And these are just a few examples. And you can imagine how this could be used in almost every area of our real life. And so the goal of my research is to solve the fundamental challenges in computer vision that we need in order to enable this controllable generation of the 3D world. And so I want to describe towards this end, I'm going to talk about 3 challenges that I believe are important to reach this goal. And the first challenge is that of representation. What do I mean by that is that, so if you look at this image, we ideally want to represent all the details in this image from every viewpoint and every moment in time. But we also want to represent every object. So, for example, this car, and we want to represent the shape of that object from multiple views. And we want to have control of that representation. So, for example, we might want to represent only the coarse details, or alternatively, we might be interested in the fine details, such as the reflections of on the water droplets in this image. The second challenge is about remodeling the 3D world. Well, the data sets that we collect are really mere projections of the 3D world. We only get 2D projections of the 3D world. And ideally, what we want to do is to take these 3D projections and either reconstruct the 3D world, or, for example, if we have limited two views of this flower, we might want to generate novel views of these flowers that we have never seen before. But ideally, we want to do it in a decomposable way. So that means that we want to have a control of the foreground object, the background, like you see here. And we don't only want to do it for objects, we might want to do it for movements, for semantics, geometry, physics, and materials, and anything that can be decomposed in a semantic manner. The problem is that we have very little 3D data. Okay, so we might have very few projections or shapes, but this is very difficult to do only from these 3D projections. And the third challenge is that of generation. So you might not only want to reconstruct what is visible or what you see in the world, but you want to generate novel objects or novel scene, and you want to do it in an intuitive way. So you want to enable any human to give instructions and be able to then manipulate or generate novel objects in the world. And this is even more challenging because not only do we not have 3D data, we don't have 3D multimodal data that incorporates text and 3D. So let's talk about the first challenge, and I'm going to talk about my work on each of these areas. And I'm going to, and this is by no means, each of these challenges is by no means complete. We still have a long way to go, but I'm going to talk about my work towards solving those challenges. So the first work I'm going to talk about is that of polynomial neural fields for subband decomposition. And so traditional ways of representing signals are via discrete image grid, and these allow us to, for example, use a rich set of decomposition and manipulation techniques that we have in signal processing, such as using Fourier transform, the wavelet transform, or that of image pyramids. However, these approaches do not scale very well. Imagine that now you want to represent every point in the 3D space, and you don't only want to represent the features of color, you also want to represent density, opacity, and you want to do it through time. That becomes, that approach doesn't scale because we have a lot of data to represent. So, this is exactly the approach of voxel representation that represents every point in space. And you could also look at alternative representations of point cloud or meshes, but this is still very problematic, even if you represent points on the surface. So as an alternative, the computer vision community has come up with an alternative representation called neural fields. And what is a neural field? A neural field is simply a neural network that takes the spatial coordinates as input and outputs the value of the signal at those coordinates. Okay. So just to give an example, this point here would be represented by 0 in your neural network, and this point here would be represented as 1. Okay. And recent work has shown that these representations are actually very useful. They can handle RGB signals as well as signals that are not represented on a regular grid, such as 3D shapes. They're very compact, memory efficient, and they can represent high fidelity signals, and they're also very easy to optimize and regularize, as with every deep neural network framework. And so these have been shown neural fields have been shown to be useful in a variety of applications, such as 2D image fitting, 3D shape fitting, and novel view synthesis. The problem is that these neural fields are black box. Okay. As such, we can only obtain information about them by querying them at specific spatial coordinates. Okay. So, and this hinders many applications. So, for example, if we want to enforce constraint on the signal, then this is difficult to do. If we know that the signal, for example, is band limited by the Nyquist rate to avoid aliasing, then representing it with a black box neural field makes it difficult to do. And second, it is difficult to decompose the signal into different manipulable components. So, for example, an image can be decomposed into low frequency structure and a high frequency texture. But with black box neural fields, this is difficult to achieve. So the question is, can we enjoy both worlds? On one hand, we want the advantages of discrete representations that allow us the ability to decompose and manipulate signals. But on the other hand, the advantages of neural fields. So previous approaches, you might be familiar with the approaches of Siren or Fourier features. They are only able to approximately control properties such as frequency, but they're inherently black box. So we cannot enforce constraints on the output frequency or output decomposition, and they're not decomposable and manipulable. And recent work of Bacon was proposed, where we still have the situation where partially black box, but we can enforce some constraint. For example, we can enforce the upper bound limit on the output signal, but this is still not decomposable and manipulable. So in this work, what we attempted to do is to open the black box of neural fields. So that in particular, we wanted to represent signals as a sum of different neural network branches. And each branch is guaranteed to represent only one component of interest. And each branch should be manipulable in isolation. So for example, here, one branch of the network outputs high frequency details and another outputs low frequency structure. Okay, so how does it work? The network takes as input spatial coordinates x, and x is passed through a basis encoding that consists of a range of functions of interest. So for example, this could be functions of a particular frequency band. And next, the input is passed through a composition of polynomial layers composed on top of each other. And what we would like to do is, given the input subband, which is the result of passing x through the basis encoding, we would like to be able to control the output subband after passing through a number of polynomial layers. So how can we do this? Well, because composition of polynomials is polynomial, what we show is that we can simply analyze each polynomial layer in isolation. And in particular, we need to look at two particular operations that are performed in a polynomial layer, and that is either a multiplicative or additive operation. Okay, so in particular, given input f1 of x and f2 of x, we want to be able to analyze the output of these two operations. Okay, so what we do is we prove that as long as the under some condition, as long as the basis that we are looking at is closed under multiplication, then we can explicitly control compute the output subbands using the input subbands R1 and R2. And this applies for many basis functions such as the Fourier, the Gabor, and spherical harmonics, and many more.
What do you mean by compute?
Compute, you want to have an expression that is exactly a function of R1 and R2, an analytic expression of the output. I'll give an example, so it'll be clear. So if we look at the Fourier, let's look at the Fourier example. And this is one way to tell the Fourier space, where on the y-axis you get the angle, and on the x-axis you get the length of the length. And now if the input lies in the orange region, R1 or R2, then the multiplication of any input in R1 or R2 will result in the green region of the frequency band. Okay, and we can compute that exactly as the orientation here will remain the same, and the output length will be simply the output of simply a sum of the input lengths, alpha 1 plus alpha 2 or beta 1 plus beta 2. So that makes
But if you have m coordinates and high degree polynomials, then you're going to get exponentially many monomials.
Yeah, so you can, this is just one operations, but we can, each of these operations we can analyze, so we know exactly where the output would lie after each of those operations, right? Okay, let's take it off. So let's look at an example of 2D image fitting. So ideally, we want to decompose the high frequency signal from the low frequency signal. Let's assume we choose a basis function of a Fourier basis, and we use a pseudopolar coordinates for our subband design. Then how can we, and we want to fit this this image on that we see on the right side. Then how can we do this? We pass input X through a basis encoding layer that consists of the functions here you see in red. So those are particular functions, particular frequency and orientation. And X is passed through this basis encoding, and after applying a linear layer, we can explicitly we explicitly design the linear layer so that the output lies in the blue region of the frequency band. Now X is passed through again through the same basis encoding, and we perform a weighted multiplication between the output of the first layer and the input of the second layer that again passes through another basis encoding layer. And this gives us an output in the blue region of the frequency band. And now we pass X again, but through a different basis encoding layer. So these consist of a different range of functions in a different frequency band. And we can continue this way, adding more and more layers, and the output will each time be in a different range, different frequency band. So now this gives us basically a decomposition along one orientation of the frequency band, and we can simply add those the outputs along this decomposition to get an output in the blue region of the frequency band. And now if we do this for every orientation, we design a neural network that does this for every possible orientation, then we can cover all the possible frequencies of the image. And in order to fit the image that you see on the right, what we need to do is simply train all the polynomial layers, all the linear layers in this case, simply using gradient descent and a reconstruction loss. Okay. So this gives us a decomposition of the neural fields into different components. For example, here, each neural network outputs only values in a particular frequency band. Now, instead of reconstruction loss, what we can do is use a different set of losses in order to manipulate each of those branches in isolation. And then we can get a different, the output will be of a different frequency. So if we use a textual loss and that you see here, to now if we only use 3 networks that are of lower frequency, then we get a different output. And similarly, we can only use a smaller range of frequencies by limiting the network branches that we use. So given those advantages, it's still important to retain the merits of neural fields. So particularly, we want that we want them to be very expressive and compact. And this is what we show here. So on the left bar chart shows that basically we can reach state-of-the-art performance on image fitting. So that means it's very expressive. And on the right chart, we see that for this task, we use a very few number of parameters. That means that it's very compact. At the same time, we still get this decomposition that I've shown. And so here you can see a qualitative result. So you can see that because we are more expressive, we can, in comparison to the baseline, we can capture much more of the details at a different frequency. And another advantage is to being compact and expressive is that because we have this decomposition, we can converge in a much fewer number of iterations. Okay, so you can see here that already at 20,000 steps, we can fit the signal of a Thai statue in much more details compared to the baseline. Okay, so that concludes the first part, and that is of the challenge of controllable representation. And I've shown basically how you can represent signals and be able to control the signal based on different basis functions, for example, that of the frequency band. Any questions up to here?
Just maybe one. How do you make sure that there's no overlap between frequencies when you compose them together?
Yeah, you have to basically you have to design depending on the input basis function, you have to design the decomposition in a way that the multiplication of R1 and R2 will lie in the desired output subband that you are interested in. So you cannot choose any decomposition. You have to, but for specific decomposition, you can get it in such a way that the output lies exactly where you want. Yeah. Okay.
So what's the procedure for input?
Yeah, so the input is just spatial coordinates, right? So
Precision. How many bits?
How many bits? So how many bits to represent the signal or to
Input X.
the input is just so for example in image fitting, if it's a 2D image, it's just XY coordinate.
So it's
so
a pixel, it's an integer in the pixel.
It's yes, it's an XY. Yeah.
So the degree of the polynomial is like the number of pixels, or
Polynomial takes the XY coordinate as input, and then
no, but the degree of the output that you get is like the number of pixels in the image.
The degree along the layer is a hyperparameter. You can choose what it is, right? But the output is whatever the desired signal you want. So if we want image fitting, that would be RGB. That would be just 3. If you want to do represent a different signal, that could be a different output. So for example, if we want to represent a shape, for example, then one way you can represent it is whether a point is inside the shape or outside the shape. So that's a single number.
Okay, so maybe I need to understand. It seems to me that you managed to represent the image by polynomials in the input coordinates.
Yeah, you have a basis function.
I mean, very high degree. I mean, I don't see where the saving is in some sense, because it seems to me that you need very high degree polynomials to be able to distinguish different shapes.
No, so the only thing So the only thing you need is the weights of the polynomials, right? So these are the, and so if for example, so the polynomials allow you more expressivity, but for example, what we use is just linear layers for each.
So maybe I'll ask you differently. Is it difficult to cheat, like to give different inputs? I mean, you cannot compress all the.
No.
Right, so is it to cheatable? No.
It depends what you mean cheatable. So like if it's if you query it outside of what you the signal that you actually fitted, then of course the behavior will depend on we don't know what's going to happen there. So for example, if I train a particular image grid and you now query it outside the image grid, then we don't know what's gonna be happen there. But we know that the overall reconstruction loss is very low for all the points that you have supervision for. And also what we show in the paper is that you can also do interpolation very well. So even if you have points between points that you don't supervise, then you still get a very good representation. Okay. So we talk about a controllable representation of the 3D world. And now I want to talk about the second challenge, that of decomposable remodeling the 3D world. And just to remind you, we only have 2D projections as input, as our data sets, and now we want to somehow remodel the 3D world that created those snapshots or observations. And one way we can do it is by reconstructing it. Another way is by producing novel views. And I'm going to concentrate on this problem of controllable, decomposable novel view generation. And so here I'm going to talk about my recent work on volumetric disentanglement for 3D scene manipulation. And the input is basically a set of views. So we can see here, for example, a set of images of flower, as well as the object we want to disentangle. And the output is basically this object, a novel views of the entire scene, as well as novel views of the background and object in isolation. And given this decomposition, we can then perform multiple tasks. So for example, we can resize or transform each object in isolation. So for example, we can transform this TV screen, or we can manipulate this object of a trunk according to some input text prompt. And so previous attempts, such as NERV, have no object control, and some an object NERV requires additional 3D data in the form of bounding boxes. So how does it work? Ideally we want to let's begin by a representation of the full scene, and we want to represent it volumetrically. So imagine that you are looking at the scene from a particular viewpoint and direction, and now you're shooting a ray through the volume from that viewpoint and direction. And now for each point along the ray, you sample points along the ray, and for each point you predict a color value and a density value. And now you use this density value in order to calculate a weight for each point along the ray. And now you use a process called volumetric rendering in order to find out exactly the color at which the ray hits a desired target view, the view from which you look at the scene. And in order to train those weights, you use a process. You simply use a reconstruction loss between the ground truth color that you know, and that of the rendered color of that view that you predicted. And so that gives us the full scene. So, for example, the scene of this scene here with the leaf. And now, if we want to reconstruct the background, we use a mask rendering loss. And in particular, if a rendered point lies in the mask region, then we don't reconstruct it. Here it is the blue box. And if it lies outside of it, then we do reconstruct it. And because of the prior that is induced through our volumetric rendering, then you can see that it is able to in-paint the background very well. So how now, if we want to perform decomposition and manipulation, then we have the full scene, we have the background scene that we represented volumetrically. And now, in order to get a representation of the foreground, we can simply subtract the background from the full scene. And more specifically, the way we do this subtraction is by considering the weight and color of each point along the ray, and then simply subtracting the weight of the background from the weight of the foreground, from the full scene, and similarly for the color values. Now what we can do is we can simply modify those weights and colors for each point in isolation, and this gives us a modified foreground volume, and we can then add it back into the unmodified background volumetric representation. So if you like, this is the important slide about what this work does. Is simply volumetric manipulation. So once you have a volumetric representation, you can simply add and subtract volumes together.
Yeah, so I have many questions. I just want some things. So how is background defined? What is the definition of background?
So background is
just to add the question. You are assuming that sort of there is an order. There is, an object cannot be sort of both in foreground and background. Like cannot sort of playing both sides.
Yeah, I make the assumption that you have the foreground object, right? And it's completely masked by the way we represent it is by saying the projections of that to the input views is exactly the region that you masked. Okay, that makes sense. So if you had a mask, right, that describes the object in
the
input view.
Manually? This is you do it manually, or is it something that automatically the program looks at the picture and decides?
Yeah, you can use an off-the-shelf 2D background foreground software, and that works fine. Or you can by yourself draw it. It can be a coarse mask. The important thing is that you capture the foreground object that you want to remove. So that could be. I hope that.
So, because in the picture that you showed, like there's like a continuum of things, right? I mean, from the foreground to the background. So.
Yes, because we have multiple views, right? Then if you depict the object that you want for multiple views, then that gives you a representation also of the object in the volumetric sense, in the 3D sense. Okay, so let's look at one example. Let's say you want to transform the foreground object, and what we assume here is that we take the same camera parameter rays and sample points along the rays, and now and if we have a transformation T, we can simply query the points and the inverse of this transformation to get a modified foreground volume. And then we can add it back to the background scene, which is queried at the input coordinates. And what this gives us is this transformation of the foreground only. So you can see that we transformed here the object of the TV without and while capturing the reflections correctly, which are part of the background representation. What about semantic manipulation? Let's say you want to manipulate this volumetric this trunk of the tree using different text prompts. Then we talked about the background scene, and we talked about the mask rendering loss that we use for the background, but instead we can use a semantic loss here. And more specifically, what we want to do is we want to have we want to render from a fixed volume, we want to render the background. That is a volume that doesn't change, but we have it. And for the modified volume, we want to render exactly the object that we want to manipulate. And what we do is the output is passed through a multimodal similarity loss with the target text that we desire. So for example, if you wanted to be similar to an old tree, you would get the similarity loss would give you a high score if the output is similar to that, or a low score otherwise. You also want to make sure that the background stays the same, so you want a reconstruction loss between the background of the modified volume and the background of the text volume. Okay. Okay, so this concludes the second challenge of
We need to ask in English or in Hebrew.
you can talk in Hebrew.
מה היתרון של הגישה שלך לפני, ראינו כבר רקע ושינוי של רקע, מה היתרון של הגישה שלך? בחלק הראשון הראית לנו השוואות, אבל מה כאן היתרון של הגישה שלך?
היתרון הוא שיש לך אפשרות לעשות editing volumetric של האובייקטים, אוקיי? אם אני מסתכל על שיטות 2D שעושות in-painting, אז אם נגיד יש לי חלק מהאובייקט שהוא occluded פה, אוקיי? אז לא יהיה לי ייצוג של האובייקט ברמה הווליומטרית של זה. פה אני יכול ממש לזהות סדר של דברים. זה לא יפה. כאילו, היו שיטות שהשתמשו ב-additional 3D information, כמו bounding boxes והרבה יותר, אבל פה אנחנו מייצגים שיטה שמשתמשת ב-2D. Okay, so now I want to talk about the last challenge. So we talked about how we can decompose the world, but from 2D observations, we want to reconstruct it, and we want to be able to do it in a decomposable way. So the last challenge is about how we can now generate novel content that we have never seen before. Okay, and we want to do it using some intuitive manners. So, for example, using text or instructions. And here I'm going to talk about text to mesh. And here the idea is that you get an input 3D object, such as the mesh you see here on the left. And what you want to do is, given a target text prompt, you want to stylize it according to that text prompt. Okay, so here you can see a few examples. And just to put things in perspective, you might have seen a lot of work recently on text to something. So in 2D, there has been a number of works now and that do remarkable jobs. Those examples here. But in 3D, where our work was the first to do a 3D stylization from text. And subsequently, since then, because there's been really an explosion in the field, we have seen other works that have looked at generation of shapes as well from text. So intuitively, you can think of it in a very high level as imagine having a conversation with someone and someone tells you about this large concert hall with many floors. And in your mind, you can have pretty good visualization, a 3D model of how this concert hall would look like, right? In the context of augmented reality, imagine that you take a picture of an object, and now you want to manipulate it or change its style using some instruction. So the stylization captures a number of important components. For example, here, for the example of Iron Man, you can see that it captures, produces hardware global semantics. So you can, for example, we're able to produce realistic muscles, clothing, materials, and different textures. For this example of color for shade, then you can see the ability to imagine a variety of different textures. For brick lamp, then you can see that even though we only produce stylization, then the network, I'll tell you exactly what it is, but we're able to produce a realistic hallucination of how light would look like inside that object. And it also enables us to generate out-of-domain objects, such as an astronaut, of course, that doesn't actually exist in real life. So how do we do this? The idea is that the intuitive idea is that we have, the setting is that we have a 3D object representation, we have a user input, and we want to edit that 3D object. And more specifically, the input is a 3D object that we represent using a mesh, and we have a target text prompt. And we begin by passing the mesh through a network called a neural style field. And what is that neural style field? In particular, it's basically a neural network that takes as input spatial coordinates, in this case, X, Y, Z coordinates, and outputs a style. What is a style? A style is both an RGB color for every point, as well as a displacement value. Okay, so a displacement is basically you can consider the normal of each point for normal of each vertex, and as long as what you want to do is you want to walk a distance d along that normal to get a new vertex, and together this represents the style of the style of the mesh.
Like a warping of the original mesh?
Yeah, so you move each vertex along this normal, and you change the color according to the predicted color. Okay, so now the next stage is what I call a neural rendering on an augmentations component. So in particular, we have a 3D mesh and we want to convert it to a 2D representation. So one way you can think of it is that we can simply rotate the camera and take pictures of it from multiple views, right? And this process can be done in a differentiable manner. So using by rendering multiple views of that input mesh. And once we got the different snapshots or views of this object, we can simply apply another set of data augmentations, such as the local augmentations and global augmentations. And this is a sort of a 2D representation of a 3D object, if you like. So once we got this 2D representation of the 3D object, we want to compare it with the input text. And the way we do that is using a semantic loss. So in particular, for each of those images, we pass it through a semantic loss component that gives a high score if the image is similar to the target text and a low score otherwise. And this is what drives our, by using this loss, we can improve the weights and of the neural fields to give us a better style.
Who supervises this? Who gives the score for the?
Yeah, this is the semantic loss. It's basically an off-the-shelf a pre-trained network that was trained to give a high similarity score to images and text that are matching semantically and low score otherwise. So,
And it can also do it for objects that don't exist.
You cannot do it for objects that don't exist, but you hope that the network, by seeing enough examples, it can generalize also to understanding of text and images that we're not seeing in the training set. So in particular, maybe an astronaut course. Okay. So as I said, there's no 3D data set here. And here you can see some results. So yeah, so let's see. So for example, here for the input of a shoe, then we can see the stylization of a cactus, a bark, or brick. Here you can see a few other examples. And because
Can you explain what is the data set that you did use for that use?
so there's no data set at all, because, well, it's a bit of a cheat. It's not really no data set. We had there was basically a network that was trained a priori to basically give on input images and
I'm not
text.
talking about this money.
Okay.
I'm talking about how we generate this. So you added this to have like a data set of meshes, right?
No, this is overfitted on a particular mesh. You can use any mesh you want,
Okay.
but this network is trained on one mesh.
This time you give it a mesh and then you train it.
Yes, this is a test time of optimization on a particular mesh and text. There's no data set here.
So you have a mesh of a camel?
Yeah, the input is a mesh, right? It's what you want to stylize.
The camel.
Let's say the camel
semantics
here.
of the camel is given by the mesh. You don't need to create a camel.
You don't need to create a camel, right? But subsequent work try to also create a camel, but this here you're given the camel, you want to change just the style. Okay. And okay, so here you can see the ability to also to morph between different text fonts, right? So you can represent the style of one, and now you can simply morph between them. What about humans? The interesting thing, we took a mesh of a human and we asked it to stylize it like a Steve Jobs or Hulk or Batman and so on. And you can see because the similarity loss has an understanding of individual people, and it was able to have a stylization of how Steve Jobs, how he thinks Steve Jobs could look like. We also wanted to see if there's we can increase the granularity of text, and that could be represented by the style that we get. So we may start with something like a lamp, and then add more details, such as a luxo lamp, a blue steel luxo lamp, or a blue steel luxo lamp with corrugated metal, and we can really capture all those details in our stylization. Now, I talked to you about semantic loss between images and text, but because this is a multimodal loss, we can also compare images to images. So what if we, instead of using text, we use an image, then now we can also stylize meshes using images. So given this input mesh on the left and this desired style, we can now stylize those meshes accordingly. And we can even go a step further and stylize the content mesh using another input mesh that you see here.
Is there a semantic loss?
Yeah, we still use a semantic loss, but here you basically render the style mesh from multiple views, and you can then compare it to the content.
But you don't have clip for this. Like, you can't use like a clip semantic loss for.
You can, because what we did, if you see here, then for the mesh, we can simply render it in the same way that we did for the content mesh. We take multiple views, augmented, and that's a representation of the style mesh. And now we can simply compare the content with the style.
What text do you feed to clip?
So this is just an more mesh to stylize.
No, I'm asking. Yeah, I was asking if you're using clip here.
Yes, I'm using a semantic loss that I'm using clip because it can also get just images.
Oh,
right?
image to image.
Just image.
Okay.
Okay, so just a quick word. We recently also considered this similar setting, but not for 3D meshes, but for objects in videos. And the overall idea is similar. I won't go into details here, but we similarly want to render the object in the background for multiple views, and we use the similarity loss to stylize objects in the videos in this way. Okay, so this concludes the third component, and that is of giving an intuitive interface for controllable 3D generation. And I'd like to summarize. So we talked about controllable 3D generation, and I talked about multiple challenges. The first challenge was on controllable representation of the 3D world, and we talked about how we can open the black box of neural fields. And the level of control that we have here is the low-level signal control using a basis such as the Fourier, the Bohr, spherical harmonics, and so on. We talk about decompositional remodeling, decomposable remodeling of the 3D world. And here I've shown how we can generate novel views in a compositional, decomposable manner. But the type of control that I talked about is high level, is an object level control of objects. And the third challenge was that of an intuitive interface for controllable 3D generation. And we talked about how we can stylize objects using text. And here, we had a control of style using high-level semantics, that is of text. And you can imagine how this table could be instantiated differently, right? So for example, you could look at, for example, deformable objects, and you might want to be able to control their motion. And so this idea of having control is important for all the levels of both from low level to high level, and we can look at different tasks in this case. So what's next? I just want to quickly mention some things that I'm excited about. So we talked about all the different transformative applications that controllable 3D generation can enable. And I just want to touch about a few of them. Imagine that you want to design your living room. You have this ugly living room, and now you want to turn it into a much more beautiful living room. And maybe it's beautiful. Okay, so the question is, let's say I want to place this object in the scene, right? And now I cannot just place it there volumetrically. I also have to understand how light affects it and how it and light may affect different materials in a different way. And if I want to do it in a realistic manner, I have to be able to model the properties. If I want to put a transparent object or design myself this vase, then I have to understand how light passes through transparent objects, and particularly how that interacts with the rest of the scene. Let's say I want to move objects and place them in a different position, right? And now I'm talking about the ability to understand volumetrically how I can move objects, and potentially I need to understand physics because I want to place objects on top of another, and how's that going to affect things? And all of this, we want to do it in an intuitive manner. We want to do it to enable every person out there, even a non-expert, to do it using a conversation. So this could be using text, but it could also be using hand gestures. It could be using your voice. You really want to be able to do this to give any person this ability to do it. A second area that I think this is exciting is generating photorealistic simulations, for example, autonomous driving. So imagine you can see an example of sort of a dangerous situation or a difficult task for a self-driving car when someone just approaches it from the left. And if we can sort of generate, disentangle, and manipulate shapes, textures, and the movement of all objects in the scene, then we can potentially generate infinite and diverse photorealistic simulations, but we can also generate those hard examples that are at the tail of the distribution, those that will make it difficult for the self-driving car. And towards that goal, we looked at the setting of image classification, and we looked at how we can semantically manipulate objects to full image classifiers. And the last, another I'm excited about is that of analysis-based synthesis. And what I mean is, if we look at this image of people sitting in a cinema, and you and I can perfectly understand every one of those people in the cinema, and we can segment it. But an off-the-shelf object segmentation cannot do so very well. Similarly here, the prior that you have about humans tells you there's probably humans inside this box, right? But if I look ask an off-the-shelf object detection, it will tell me there's just a box. There's no understanding that there are humans inside. So if we can design generative models that enable us to either view this cinema room from a different angle or generate plausible realization of different angles, as well as a potential control or disentanglement of what could be inside this box and outside this box, then potentially we can get a better understanding of the world. And this similarly holds for imagining the setting of robotics, where we have to navigate a scene and we see different objects. If we could hallucinate or imagine what could be behind that object, then that could potentially enable us a better representation for navigation. Okay, so I'd like to thank my collaborators and especially my supervisor, and I have to take questions.
So you showed us 3 different examples, and for each one, it seemed like there was a different internal representation of the object, and everything was completely different from the other 2. Is there any hope of having one grand unified solution here, kind of like value does everything that you would want to do with generating images?
I don't think there is. That's also why it's interesting. There is no one silver bullet for the representation that you want to use. If I want to represent novel views and I want to do it in a photorealistic way, then it would be wasteful to reconstruct the 3D object completely. Okay, so think about it this way: you would have to either have much more data, 3D data that represents the object from multiple views, and that's difficult to get with something like DALL-E because we have limited 3D data, right? So it's kind of what you want. If you want to photorealistic multi-view, then it doesn't make sense to reconstruct the 3D object, the 3D object from all the views and will give an explicit representation, because that would be, you'd need a lot more data for that. Okay, so I think it's basically choose the right representation for whatever task you want to perform.
So I'm going to have to go to a different tool. There will be like a down for this, and a down for that, and one separate thing for each task.
You wouldn't use so you wouldn't use I wouldn't use the same. I mean, you could use DALL-E to perhaps this. You can use DALL-E to derive to learn a useful 3D representation. Yeah. I don't think there's one single representation that you can use. Like, for example, if I use, I know how to, there are representation of humans that are highly detailed, where you represent all the joints and you have very good models for facial, for the faces. But so these are useful for certain settings, right? Because you might want to have a perfect reconstruction of that. But if we now want to, if you're going to use that representation now for vast scenes with multiple objects, and we're going to have to design such a model for every one of those objects, I think that it doesn't make sense. So I think it makes sense to use a different representation for whatever task it is that you want. You can distill it from DALL-E. And that's what makes 3D a lot harder. In 2D, you have an image, you have pixels. That's what you want to generate. 3D, there's different ways to represent the 3D world. And using one representation to me doesn't make sense.
אני רוצה לשאול על הישימות של השיטות שלך. אין ספק שבשביל לייצר סוס אסטרונאוט זה עובד, והרקע זה שהורדת את הפרח והרקע זה מאוד שיט. אבל בוא ניקח למשל את המוח כאן. איך זה רלוונטי? הלוא אתה רוצה מודל של מוח של בן אדם שאתה הולך לנצח בדיוק עצום, הלוא שגיאה של מילימטר היא קטלנית.
נכון.
איפה השיטות רלוונטיות לזה? אתה לא רוצה לקחת מוח של מישהו אחר.
כן, השיטות שהצגתי פה הן לא ספציפיות למוח. במוח אתה רוצה שליטה שהיא הרבה יותר fine grain.
נכון.
יפה, אבל יש לך כבר שיטות ב-images, לשלוט ב-fine grain details generation, ממש ברמה של הכתף של הציפור. אני מאמין שאתה יכול לקחת את השיטות האלה שעובדות ב-2D, ולקבל את אותו level של קונטרול גם ב-3D.
בלי לקחת את המודל המדויק של הבן אדם.
אז זה תלוי מה אתה רוצה, אז אם אנחנו מדברים, אם אתה רוצה, זה תלוי מה אתה רוצה. כאילו אם אני רוצה עכשיו בן אדם עם היכולת למדל את כל התנועות שלו ואת כל ה...
לא,
זה משהו אחר. את הבריין.
את המוח של הבן אדם הספציפי הזה. אז איך אני משתמש בשיטות שלך כדי להשיג מודל יותר טוב של המוח הספציפי של הבן אדם הזה?
אז מה אתה רוצה לעשות איזושהי ויזואליזציה של המוח, אז יש לך, נגיד, לקחת כמה, יש לך תמונות שמייצגות את המוח, אתה יכול לייצג את המודל תלת מימד, נגיד בצורה וולומטרית, ועכשיו תלוי מה כאילו, האינפוט שלך הוא שונה, אני דיברתי על אינפוט של נגיד טקסט או מאסק, האינפוט שלך יכול להיות פה נגיד איזשהו, לא יודע, איזשהו חיווי אתה יודע, במהלך הניתוח של משהו שקרה לו, אז האלמנט הזה צריך קודם כל כאילו לדבר עליו, איך החיווי הזה כאילו נותן לך שינוי בתת מימד, אבל אני חושב שלמדל את השינוי עצמו אתה כן יכול לעשות עם השיטות שתיארתי.
אני שואל על הדיוק.
מה שדני מציע, אני חושב שהוא בעצמה מצוינת, כי המודל הוא מאוד מדויק, ויש לך פרוגרמס בקראונד. במוח שלך הרבה אזורים, בדיוק השיטה שהצגת יכולה לפרק את המוח בכל האזורים שלנו. במיוחד אם יש לך איזושהי סגמנטציה מאוד מדעית שיש במודל אחר שנותן, זו בצורה מאוד מדויקת.
אבל מה שאני שואל אתכם זה, האם יש סיכוי להפעיל את הטכניקות במקומות שבניגוד לדוגמאות,
נרף זה מאוד מדויק, לא משנה. נרף זה ייצוג מאוד מאוד מדויק, מבחינת הפרימן.
לא, אבל פשוט דה פקטו זה בשיטות מסורתיות.
אבל נניח משימה של פיגמנטציה של מוח, שיהיה כל האזור בנפרד ונרף, ניתן לסגי להמשיך תשובה, כי אני לא רוצה להשתלח, אני בודק מתפקתי.
כן, אני חושב, אוקיי, אז בנפט אתה צריך, כאילו, יש לך את הדגימה של הקרן, כן? אם אתה דוגם אותו מספיק צפוף, אז כן, יש לך find and change.
אין לי ספק שיש שיטות, השאלה מה זה מוסיף על השיטות הקיימות למידול של המוח, כשאתה הולך לנתח עליו.
מה שזה מאפשר לי, מה שאני מדבר עליו זה היכולת to control, to disentangle, כדי לשנות ולהוציא. נגיד עכשיו יש לי אזור במוח ואני רוצה לזהות מה יהיה אם אני אוציא את האזור הזה מבחינה זה, ועכשיו אני יכול לזהות מה יהיה כאילו מאחורי. אוקיי, אז הרעיון הוא control, הרעיון הוא שאתה יכול לשנות או to control volumetrically את מה שאתה רואה בצורה שהיא אינטואיטיבית.
אני חושב שלא.